Let us start the discussion on operating systems today. In our introductory lecture, we had identified two major objectives of the operating systems. The major objectives are, as has been noted down here, that to offer the user a hospitable interface and to provide a comfortable and convenient runtime environment. Now, as we told there, the bare hardware is though powerful but extremely difficult to use, and therefore operating systems basically gives layers of softwares to give the user an extended machine view where the user gets a comfortable user interface. And the second objective is to manage the system resources towards their optimal use. Let's see what are the system resources. We also identified what are the system resources. Let me show it once more here. The system resources are categorized into these four types. One is a processor, second is the memory, third is the devices, and four is the information. And the management functions that the operating system has to do is that to keep track, that is, for example, in the case of a processor, it has to keep track the status of the processor, okay, whether it is in use, whether not in use, such informations, then decide who gets and how much. For example, in the case of a processor, that of the many systems, many programs that will be running, it decides which program gets the processor, for how much time that it gets the processor, and so on. Now, once it decides that which program gets the processor, the OS allocates the processor, and on completion of the job, or if necessary otherwise, it deallocates the processor from the program. That is true for memory, devices, and information. Therefore, these are the system resources mainly, and these are the management functions that the operating systems has to do. And the objective here is towards their optimal use. Okay, the system resources should be so utilized that the resources are utilized optimally. Now, before we proceed any further, let us define what we call a process, a much used term in terms of the operating systems. Now, we are familiar with program. The program is that what we write in some high level language or low level language. Okay, it is a passive entity in the sense the program as such is not executing. Okay, the program is there, ultimately converted into a machine language. The different functions, etc., are bound together, and it is, say, ready for execution. A process is a program in execution. Naturally, it has something more than it is a passive entity, that it includes the current activity. What are the current activity it includes? That value of the program counter, since it is executing, the program counter will have a value that is included in the process corresponding to the program. Contents of processor registers, because all the processor registers are holding intermediate results, and therefore that contents of the processor registers are also included in the process. The content of processor status word, which we described in our previous lecture, that this processor status words in fact keeps track of all the condition codes that interrupt mask, that interrupt whether the system is enabled for interrupt, you can accept interrupt or not. All these informations, for example, whether it is in user mode or supervisor mode, all of them taken together we call the processor status word, and that is also a part of the process. Apart from that, the process stack that the process uses, which contain the subroutine or function parameters, temporary variables that the subroutine of the function uses, the return address, etc., all these informations are in the stack process, and that's also part of the process definition, and naturally the data section. Okay, that's the process. Therefore, so when we have a program and when we run the program, a process is created, and the process includes all of them. Okay. Now, when a process is in the system, that is in executing, that is it is in the state of execution, or possibly it is executing, that means the CPU is executing that. Okay. Now, the process in the system goes through several states. We showed in our introductory lecture that a 5-state process diagram, state diagram. I am repeating the diagram here. See, if you have a single job, okay, which has been submitted to the system, then firstly that the operating systems will admit that job, and it will be in the ready state. Therefore, when it is submitted, it is in the new state. Then when it is admitted into the systems for possible allocations of the processor to the process, it is in the ready state. Now, if it's in the ready state, then it can be dispatched to the processor, okay, and comes in the running state. The CPU is executing it. Now, while executing it, naturally the process will try to execute many IOs. So when an IO is executed, in that case, that on that IO, it comes to that waiting state. Okay, because this particular process cannot proceed anymore, right? And therefore, this process which was in the running state comes into the waiting state. Now, it will possibly be taken out of the waiting state by some interrupt that the device gives. Okay, that device issues, and the CPU takes it, and this process will be taken out of that waiting state and put back into the ready state on, say, IO or event completion. Now, sometimes, not only for that IO, for other events also, the process gets in the waiting state. Okay, for example, say the part of the data is not in the memory, a part of the instructions, the program's address space, processor's address space is not in the memory. Such situations also, it comes into the waiting state. Okay. Now, this way it goes on. It's once more dispatched until the process is complete. Okay, then it is released and comes into the terminated state. Now, this is so far as a single process if it is in the system. Naturally, you can see immediately that if the process is waiting for the IO to be completed or event to happen, okay, and if it's a single process only that is within the system, right, then naturally the CPU cannot have any process which is in the running state, and therefore the CPU remains idle. This is a tremendous wastage of resource, and as such, it's never mostly that a single process that runs in a system. This leads to the concept of what we call that multi-programming, where more than one processes are created out of a single program or out of many programs that are submitted to the system. In such situation, naturally we need to have another transition from running state to the ready state. The reason being that, so for example, a particular process has been given the CPU, okay, dispatched to the CPU. It is running, and it is essentially a CPU bound job. That means it's a compute bound job. It is continuously computing for quite good amount, for quite a good duration. In that case, all other processes will be waiting only. Therefore, in such situation, what generally is done is that when the process is dispatched to the processor, a timer is set that this process should run maximum, say, for some millisecond, okay, or some microsecond. Now, the process goes on running, that particular process in the running goes running in the central processing unit till an IO happens, and that in that case it comes to the wait state, and one other process which is in the ready state is dispatched to the processor immediately, so that processor is never idle, okay, until and unless we do not have any process in the ready state. And in the meantime, that means the time interval that was allocated to the process, if the time interval is over, and within that time interval, no IO, this particular process issued, no IO request this particular process issued, in that case, that process is forcibly taken out of the processor and it's put back into the ready state, okay? And another process is given a chance to have the processor. That is why, in the case of a multi-programming environment where more than one process are there in the system, then there is another transition, we call that timer interrupt, okay? The process can be taken out of the CPU, that means the running state, and comes back into the ready state. You see, at the same time, that if a system has many processes, then the situation is that the different processes will be in the different states. Okay, some of them will be waiting for I/O to be completed, and some of them possibly waiting for the same device which has been occupied, which has been attached by some other process. Okay, therefore, there are many reasons that the processes get in the wait state, and there may be, therefore, many due to the many reasons, there may be created many wait queues. Okay, instead of one wait queue that is here, many wait queues are created. That means a process which is waiting for a particular event, all the processes which is waiting for a particular event will be put into one wait queue. Okay, so there may be many wait queues. Similarly, many processes may simultaneously be in the ready state, and therefore there should be a ready queue where the processes which are in the ready state are kept. The scheduler, we call a scheduler, that takes a process out of the processes in the ready state, okay, and is dispatched to the processor. What is a scheduler policy, etc.? We'll discuss it later on. Now, this, in fact, if we keep this in mind, that this, which is an important diagram, the process state diagram, that the processes can be in different states, then we'll have to see later on that what actions are taken at the different states. Okay. Now, depending upon this situation, the processes may be broadly classified into two categories. One is called that IO-bound processes, and the another is called the CPU-bound processes. By IO-bound processes, it's meant that the process that issues IO requests very frequently, and therefore it very frequently goes into that IO wait state, right? And in the case of a CPU-bound job, the IO requests are less. Therefore, once the process is in the CPU, okay, it can remain in the CPU for quite a long time. Now, naturally, situation is this, that if, for example, we find that most of the processes are in the waiting state, okay, and there are only few CPU-bound jobs here, the IO-bound jobs are less, then since we can expect that it will take some time for the IOs to be completed, and a job coming from, or a process coming from that IO queue into the ready queue will take some time, then the scheduler can take a CPU-bound job and give it to the processor for a longer duration of time, so that the processor remains busy. Otherwise, the chances are that the processor will go to idle state. Okay, and therefore, this is the reason sometimes that we differentiate between IO-bound job and the CPU-bound job. Now, this also can be decided a little bit, what should be said, dynamically. For example, we can see that a CPU-bound job will remain in the CPU for quite some time. And since it's CPU-bound, IO is requested very infrequently. The chance is that it will come back to the ready state through timer interrupt only. Okay. In that situation, naturally, if we find that a particular process has come back to the ready state on timer interrupt, okay, in that case temporarily we can assume that that particular process at that time is a CPU bound. Okay, that means more CPU time is needed for it. Otherwise, if it goes through this IO waiting queue and comes to the ready state, we can take it to be a IO bound job. Therefore, we can dynamically assign a particular job, okay, or flag a particular job that is an IO bound or a CPU bound, depending upon via which path it has come to the ready state. Okay. Now, naturally, there should be some scheduling policy, okay, that which of the ready state should go to the running state, and which of the jobs that has been submitted, okay, will ultimately be allowed to come into the ready state. Okay, the policies are there. We'll discuss some of the policies in the course of our lecture. Now, this gives a picture of the process scheduling queues, right? You see that here a rather simplistic diagram. We have a ready queue here where the ready processes are here. Okay. From that ready queue, a short-term scheduler takes a process and puts into the CPU. Right. If the process is over, then it exits from the CPU, or if it's an IO request is done, it comes to the IO waiting queue. Now, as I said, there will be generally more than one IO waiting queues over here. That means CPU will put into, the system will put into, the operating systems will put into the IO waiting queue corresponding to the cause of the waiting, right? It may be devices, it may be other reasons also. Therefore, depending upon the cause, into the corresponding waiting queue, a particular process will be put. Now, here is the job queue, and here is the enter. That means initially, when jobs are submitted, it is kept into the job queue, right? From there, the jobs are selected, and then it's put into the ready queue. Now, you can see there are two scheduler that will be working. One scheduler is called a short-time scheduler. This short-time scheduler takes one of the processes that is in the ready queue, okay, right? And we can arrange the ready queue according to the different criterion, like say priority, etc. That also we'll discuss. That the short-term scheduler takes one process from the ready queue, right? And since I'm talking about queue, I am now assuming that whichever is at the front will be taken out of the queue and will be put into the CPU. Okay. This, as I was telling, that this is a short-term scheduler. Depending upon a policy, it depends which should come at the front of the queue. Okay. And after deciding it, a dispatcher, we call it a dispatcher. The dispatcher takes the responsibility of taking that process and putting it to the CPU, where some bookkeeping activities have to be done before actually the process can be put into the CPU. Now, on all the job, as the jobs are submitted, as I say, that's remaining the job queue, and a long-term scheduler controls that which particular job will be taken from here. That means which job should be put into the front of the job queue, that will be taken and it will be put into the ready queue. Now, how many jobs are to be taken from the job queue, that also is decided by this long-term scheduler. Okay, which means that the long-term scheduler controls the degree of multiprogramming, because depending upon how many jobs have been taken into the system, the degree of multiprogramming will depend. Okay. Now, as we are talking, that the processes or the jobs, sometimes we'll use a term here, the process and the job interchangeably, whether no confusion can come into the picture. If you're saying that the processes will be put into the queue or the jobs will be put into the queue, but what actually is put into the queue, how a process within the system is represented. Okay, what represents a particular process? Let's first talk about it. Okay, a process is represented what we call a process control block or a PCB. Okay, now this is a PCB, right? This PCB has different fields. The first field is a pointer, that is the link to other PCBs. Okay, for example, naturally, if the systems has, naturally the systems will have many processes inside. All these processes are linked so that the system knows what are the processes that are there in the within the system. Okay. Then the process state is kept as one of the field. By the process state, we mean whether it is a new, or is a ready, the running, or the waiting, etc. That particular information at any instant of time is kept in the process state. Then the program counter, which contains the address of the next instruction that is going to be executed, it is also one field of the process control block. The processor status word, as I said, that which contains that user supervisor mode bit, enable interrupt bit, interrupt level or mask bit, condition code bits, all of them. Okay, that processor status word is also a field. The CPU, all the CPU registers. Okay, that is also a field of the process control block. It naturally it will contain the contents of all the CPU registers that this particular process is using. Okay. The different registers that are involved, as we have already discussed in our architecture class, that if it's an accumulator based system, then it will be, that accumulator will be there. That index registers, the base registers, the general purpose registers. Okay. Now, naturally, what are the registers that are there? That depends upon the architecture, and the contents of all these registers which are relevant, okay, to the process, are all of have to be, the copies of all of them are kept in the CPU registers here. Now, this is another field, that memory management information. Okay. Now, regarding that memory management, we'll be talking later on, that there are various schemes of memory management. For example, it can be that partition memory, the page map table, that means page mapped memory, or the segmented memory. Okay, this depending upon what memory management scheme we are using, that memory management information is kept here. Now, this link is a pointer to the same scheduling queue. That means, for example, if it is the ready state, that this link will be pointing to the other PCBs that are in the ready state. If it is in that I/O waiting for a particular device, this link will be pointing to the waiting list for that particular device. Therefore, this link depends upon which state the particular process is. Then the scheduling information are there. Naturally, in that scheduling information, a particular process's priority can be kept. Other informations may be kept here also. That is important and pertains to the scheduling information. Accounting information is also kept. For example, what is its job number, what's the process number, what's the CPU time used till now, till this point. The real time elapsed, that means when the job was submitted, and from that time onwards was a real time that has elapsed. Limits of time, that means how much time is permitted, how much time for this particular process, okay, the CPU time possibly, that is permitted to be used by this process, or a time limit that if the particular time limit is exceeded, then this particular process should be ejected out of the system. Such information, that limits of time can be kept as an accounting information here. Then I/O state information is also kept in the PCBs. For example, what are the list of I/O devices that are attached? For example, it may be, the process may be using the MAC tapes, Okay, in that case, what are the MAC tips that is attached to this process, that list is kept. Then the list of open files, for example, the process may be using many files in the secondary storages, okay, including database files, right? Those informations are kept in that IO status information. Therefore, you see that this process control block, if we examine the content, that tells me that all the informations regarding the process. Okay, therefore, if the operating systems, any module wants to check that any informations regarding the process, it can immediately examine the process control block and get this information. Another important thing, let me say that, for example, here, starting from this program counter to the memory management information up to this, that means program counter, processor status word, CPU registers, the copies of CPU registers, and the memory management information. These fields, okay, these fields have to have naturally has their hardware component. That means the content of program counter, if it is a particular process is executing, that means it's in a running state, then it has the value of the program counter, it has own value of the processor status word, it has its own values of the CPU registers, and it has values of this memory management information that is in the hardware. Okay, now say the situation is that it is running and it has to come to the waiting state because an IO has been requested. Then all these informations like the CPU registers, processor status word, the program counter, and the memory management informations, all of them are to be saved, okay, and they are saved immediately into this processor control block corresponding fields. And when another process has to be taken from the ready into the running state, okay, ready into the running state by means of the dispatch, then the corresponding processes, all this information, that means this program counter, processor status word, registers, and memory management informations are to be taken from its process control block and have to be loaded into the hardware registers. Only then that particular process, the second process can start executing. Okay, therefore, this PCB also has those informations which is needed to be switched when the process is switched from one state to the other state, right? And that's why you can see the process control blocks contains all informations regarding the processes management. Okay. Now here to clarify the point of the queues, say we have a ready queue here, we have kept linked list. Okay, this is the link field that we'll be using. This is the link field that we are using here. Okay, now this is the rear and this is the front. Okay, that whenever, say this is the job that will be served the next, right? Therefore, we have the front here. Any process that comes from any of the waiting or from the any of the waiting state or from the, for example, that submit state, then that corresponding process control block is created, okay, and it is chained up with this linked list, right? Therefore, the rear points to the rear of the chained or the linked list, where any new process that comes into the ready queue is linked, right? Therefore, this essentially is a linked list representation of the queue, or linked list realizations of the queue. We have a front pointer, we have a rear pointer, and all the PCBs are linked, right? This is a queue header. Similarly, this is a linked list for an IO wait, okay, for say disk number 03. This is the front, also is a linked list. This is the front of the linked list. This is the rear of the linked list. Any other process that gets blocked because disk 03 is busy will be immediately connected or linked to this list and will come over here. And this is a queue header for the linked list of all the processes that are waiting for disk 03. Okay. Now, one of the process naturally is getting the service from disk 03. Okay. Others have to wait. And once that service is over, that particular PCB, okay, maybe that particular PCB 11, that particular process will be taken out, okay, and will be sent into the ready queue. Therefore, what is intended to mean is this, that corresponding to all the states, right, ready, waiting, the new, etc., we have queues. We have queues for separate reasons also, and these queues can be kept as a linked list and can be easily maintained. Whenever the operating systems want to check, it can start with that head, that means queue header, and can check the processes here. Very easily it can take from the front, and very easily it can put a process into the rear. Okay, there may be many such linked lists, many such queues, and all the processes here are linked by means of this pointer. Okay, this pointer essentially links all the processes, that means all the PCBs that are in the system, okay, irrespective of in which state it is. Now, that's the way that we can maintain queues. In any case, one thing I should explain here, as is true for all my discussion, that whatever I am showing, so for example, the process control block, okay, or the queue that I have shown over to here, are representative in nature. Okay, naturally it will vary from system to systems, operating system to operating systems. Essentially, one should take that these are representative in nature. Now, let us come to that important aspect, okay, that context switching, right. Now, as I said, that when CPU changes from, say, a process PI to a process PJ, the state of PI has to be saved and the state of PJ has to be loaded, okay, right. Now, as I said, that state of PI and is saved into the PCB, and state of PJ is loaded from the corresponding PCB. Okay, and you can see that immediately involves a good amount, a substantial amount of overhead. That all these registers have to be saved, the program counter has to be saved, PSW has to be saved, memory management information has to be saved. Now, how much overhead? And this is an overhead in the sense the CPU does no useful work during this time. That means no user process is essentially executing, and in such a situation, it is that CPU is doing a work which adds to the overhead only. Okay. Now, this overhead time that will be dependent upon the hardware support. There are hardwares which by single instruction we can save all the CPU registers. Okay. We can save the memory management informations once more by a single instruction. Naturally, the program counter and PSW is generally saved by means of a single instruction in any case, okay, on getting an interrupt directly, right? Therefore, what is intended over here is that what amount of overhead will be, that will be dependent upon how much hardware support, how much architectural support the machine has, okay, depending upon that. For example, if one has to save all these registers by single instructions, you can immediately say that the overhead time increases tremendously. Another important thing is that many of the central processing units have several sets of registers. That means if you switch from one process to the other process, the register set is switched from one set to the other set, and therefore no saving that way is necessary until and unless the number of sets that gets exhausted. Okay, that way also that overhead can be reduced. What is the essence of this is that what is the hardware support you have, machine has, that determines what's the overhead that is involved in switching the process, two processes, okay, from one state to the other, right? Say, now since that context switching is quite a substantial, involves a substantial amount of overhead, there's another concept that has turned out to be very popular nowadays, and that's the concept of threads. Okay, the thread is a lightweight process. By lightweight process means it's a basic unit of CPU utilization, and it consists of simply the program counter, the register set, and the stack space, right? And nothing else is I mean, I should say is involved in the thread, okay? And the thread shares with its peer threads in that its code section, its data section, and resources like open files, right? Now, the thread context switch therefore requires that only a register set switch, no memory management switching is needed, okay? No memory management related task is needed, okay? Now, situation is somewhat like this. Let us say this entire thing, that the code section, data sections, and the resources like open files, the entire thing we generally call it a task, right? The situation is this. So for example, say this is a task, okay? Now these are threads, okay? This is a code section. The thread is essentially the different execution trace, okay, within the same code section. The data section is shared, the code section is shared, okay? Only say if one switches from one thread to the other, one has to switch from one register set to the other register set, okay? But no other things have to be saved. For example, no memory management related informations have to be saved, right? This, and you see that essentially threads are, since they're using the same code section, so these are peer threads which are using the same code section, depending upon which threads is executed, that execution trace is different for different threads. So for example, here this is a program counter for this thread. It will continue for some time until the thread cease to execute, and possibly some other thread will be starting executing on switch of program counter and the registers, right? That is why we say that a thread shares with its peer threads the code section, the data section, and the resources like open files. But naturally, the program counter value, the register set values, and stack space, whether the local variables, etc., have been kept, may change, right? And as such, the thread context switching takes much less time, okay, than the process context switchings, and so that that I should say the parallelism is much more easily and much more with much less cost can be maintained by means of utilizing threads rather than process switching. Okay. Now, if we talk in terms of a traditional process, which we call now a heavyweight process, is essentially a task with one thread only, whereas in the case of a threads, there is a task with multiple threads. Now, a similar situation is there in the case of a Unix operating system. You see that Unix provides us a fork system call. If you use a fork system call, right, immediately the process splits into two processes. The process in which that fork is executed, that splits into two processes, right? One is called the child process and another is called the parent process, and both of them shares the same code, same data. I mean, by share the same code, I mean that the code is copied, that shares the same data and shares the registers also here. Okay. Now, and both of them are executing simultaneously from the point onwards of fork. Okay, both of them are executing simultaneously. Therefore, you see essentially that fork splits the process into two copies and both continue to run. Now, how one knows what's the child process and what's the parent process is this. The process ID, the fork, whenever you call a fork, it returns a process ID, and this process ID we can store in a variable and can check that process ID. The child process ID is 0 and the parent process ID is non-zero. Therefore, we can possibly write a program like this, that here in this program we have called that fork. Okay, as soon as the fork is called, the child and parent process are created. The child is a copy of the parent and both of them start running simultaneously from this point. Okay, the child copy is executed also, the parent copy is executed also. Now, here we say if we put a condition that if 4 equal to 0, that means we are talking about the child, then the child will be executed. In the copy, which is the child, then this section of the code will be executed. Okay, because you know the two copies will be created of the same address space. In the copy which is the child, 4 will return a 0 value, and therefore this statement will be true, and this child process here will be executing this portion. And in the copy which is a parent, this will be false, and therefore in the parent process this portion will be executed, right? Therefore you can see immediately that the child process and the parent process now can execute simultaneously in the two copies of it, which is a situation, I should say, similar to the thread. That means, say, for example, this is the process, somewhere here the fork has been possibly executed, then say this is a parent process goes on executing, this is a child process goes on executing. On the child exiting, okay, then naturally the child is no more there, it is dead, okay, or the parent can, if necessary, kill the child also. Now, if the child here, just as a since I started the discussion, since if one wants, the child process can be replaced by means of another process, by means of executing another call, okay, that system call exec lp, that will replace a process. Okay, here the child process will be replaced by means of another process, right? Therefore, if one wants, then the child process, after creating the child process, the child's program can be replaced by means of another program, okay, by executing this instructions exec clp. Okay. Now, therefore, let me come back here. That you see that the major idea over here of the thread is this, that it's a lightweight process. Okay, it shares the task with its peer processes, and thread switching is much less costly, because only the program counter, the register set, and the stack space have to be saved or switched. Okay, and therefore, as I was telling, the concept of thread has become very popular and has been implemented in many operating systems. That's all for today.